We already know that the integral of e to the x dx is e to the x plus c. And we've known that for a while now. Today, I mean, this part of the lesson, similar to the last one, is just extending that and saying, okay, how do we take the antiderivative or the integral of a to the x, of some arbitrary constant raised to the x power? And we've got a formula for that. It says that the antiderivative of a to the x dx is 1 over the natural log of a times a to the x plus c. So it has a lot of resemblance to the e to the x formula. The integral of e to the x is leave e to the x alone. The integral of a to the x is leave a to the x alone. But you do have to multiply by 1 over the natural log of that constant base. So let's take a look at a few examples. Starting with fairly simple examples, what about the antiderivative of 7 to the x dx? Well, 7 to the x, this should be 1 over the natural log of 7 times 7 to the x plus c. And that's it. Right? If we had the integral of 5 to the x dx, well, because this is a constant raised to the x power, this will be 1 over ln 5 times 5 to the x plus c. Right? I mean, these problems can also be done with bounds on them, and I know sometimes you guys get a little upset about those, so let's take a look at one of those. What if we had the integral from 1 to 3 of 2 to the x dx? And this problem doesn't have any u substitution. This isn't anything scary. This is just a basic thing. So first of all, the antiderivative of 2 to the x will be 1 over ln 2 times 2 to the x. And then I'm going to take this thing and evaluate it from 1 to 3. And hopefully you remember from the fundamental theorem of calculus, that just means we plug in the 3, and then we plug in the 1, and we subtract. So I will have 1 over ln 2 times 2 to the third minus 1 over ln 2 times 2 to the first. Great. That means I have 8 over ln 2 minus 2 over ln 2, which means I end up with 6 over the natural log of 2. And that's the answer for this definite integral. Right? Really not a big deal, especially when we don't have to deal with u substitution. These problems are generally pretty straightforward. So I do now want to give you an example or two of u substitution showing up in these problems. So let's do one of those. So first, let's try something like this. I mean, this is a fairly common one. What about the antiderivative of 3 to the square root of x over the square root of x dx? Okay. Remember that the deal with u substitution is that you want to find something whose derivative shows up elsewhere in the problem. We hopefully remember that the derivative of the square root of x is 1 over 2 root x. So there's this feeling like if maybe I pick this as my u, the derivative of that is 1 over root x, and I've got a 1 over root x in the problem. So I will choose my u to be root x. And by the way, if you're feeling somewhat comfortable, I'd recommend pausing the video and trying this one. I feel like it's a problem we've done before. It's a problem you guys have had success with before. You might want to try it on your own now that it's 3 to the power. So my du is 1 over 2 root x dx. Then I'll multiply this 2 root x over. That'll give me 2 root x du equals dx. So when I come back to the problem and plug this in, I'm going to have 3 to the u over, and I'm going to leave the root u here. I'm sorry, the root x here. I could have subbed that for u also, but I know I'm going to be plugging in this 2 root x du. And so I'd like to leave it there so that it will eliminate with that. Right? And then I've got this constant of 2. So important point, please don't multiply together the 2 and the 3. That 3 has a power on it, the 2 doesn't, so we have to keep them separate. We'll bring the 2 out. 2 times the integral of 3 to the u du. And now and only now, we can take this integral because it's just 3 to a variable, right? So I've got my 2 from the outside. I've got my 1 over ln 3, because that's how we deal with 3 to the u, and then times 3 to the u plus c. And the final step is for me to just plug my square root of x back in. So I'm going to end up with 2 over ln 3 times 3 to the square root of x plus c. And that's the end of that one. I did want to look at one more example. And in the one more example, I wanted to sort of look at that shortcut for integrals that we've talked about. I know we mentioned it in class one time. And I'd like us to start getting a little bit more used to it. So let me start with a problem that we should already know how to do. So if I were to ask you, what's the integral of e to the 5x dx? In some sense, yes, we do need to do a u substitution on this. I would need to use u equals 5x, and we would go through all of that. But I mentioned the shortcut in class that if the thing that's being plugged in, if that has a derivative which is a constant, so like this one, the derivative of 5x is 5, when we integrate, we're just going to get 1/5 and then do this integral normally. The integral of e to the 5x is e to the 5x. So I've got 1/5 e to the 5x plus c, right? That's sort of the way that shortcut worked. If the thing that you were going to do a u substitution on had a constant derivative, you can just do 1 over that constant. Again, if you're still not comfortable with that, just do the full u substitution. It'll work. It takes a little bit longer, and so I want us to get used to the shortcut eventually, but I'm okay with you doing it the long way for now. So now what about in the context of a new problem? What if I had the integral of, I don't know, let's say 9 to the 2x minus 1 dx? The idea is in this problem, sure, we would just need to use a u of 2x minus 1. But the derivative of that 2x minus 1 is 2. That's a constant. So I could probably use a shortcut here. I could say it's going to be 1/2 times. Now, how would this integral actually work out? Because it's a constant to a variable power, we're going to have that 1 over ln 9 times 9 to the 2x minus 1 plus c. And so in the end, I'm going to end up with something like 1 over 2 ln 9 times 9 to the 2x minus 1 plus c. And in some sense, that's all I need to say in this video. I need to clean off this desk. That's all I need to say in this video. That's effectively how we take the integral of a to the x. The big thing to watch out for is just that u substitution happens, and that we do need to still be mindful of that. So that's all I've got in this video. I'll see you in the next one.